Lesson 39, day 2. For day 2, I want you to start off with this problem here, and I want you to evaluate this problem. And then we'll come together and work it out. So, cosine negative 25 pi over 6. Do I like that? Do I want to change that?
You want to change it.
I want to change it. How do I want to change this?
You want to make it positive.
I want to make it positive, but I also want to keep this angle between 0 and 2 pi. So I need to find a whole bunch of what? And possibly a whole bunch of these. Or multiple of these. When I add 2 pi, I'm finding a coterminal angle. So I'm going to find multiple coterminal angles, because I think everybody would look at that and say, hey, how many times does 6 go into 25? 4 times. That means there's 4 pi in there. Does everybody kind of get that? There are 4 pi's that go into 25 pi over 6. Because there's 4 whole 6's. So therefore, I'm not going to go around once, I'll go around twice. And then actually, I probably have to go around 3 times to turn it into a positive side. So knowing that, you could make this go a lot quicker. We're not today. We will do this the long way, and that is negative 25 pi over 6 plus 2 pi, which we don't like. We wanted to change that to what? You need to have common denominators. So times that by 6, that's 12. So when I do this, I end up with negative 25 plus 12. Negative 13 pi over 6. Not enough. Add it again. 12 pi over 6. We already did the work, so why not just reap the benefits of that, right? Now, what's negative 12 pi plus 12, or negative 13 pi plus 12 pi? So negative pi over 6. Maybe that's not enough yet, because I like to be within the unit circle. Add it again, which ends up being 11 pi over 6. So I am going to change cosine of negative 25 pi over 6. I, guys, could change that to, if I wanted to, I could change that to the cosine of negative 13 pi over 6. Or I could change that to the cosine of negative pi over 6. Or I could change that to the cosine of 11 pi over 6. And that is what I will do. This is not the only way to do this problem. I'm trying to show you the best method that will use the fact that we have coterminal angles and that I now have an angle that is on the unit circle. But wait a minute, think of it this way. If I went a negative pi over 6, I would be starting at the positive x-axis and dropping down pi over 6, which would still leave me at 11 pi over 6 on the unit circle. They are the same, no matter which way I go to get there. I now have to do the same thing for tangent. Or do I like that tangent? Is 4/3 pi okay? Okay, so I'll just leave that one. So I don't have to change that. Now everything is on the unit circle, yes? Go to 11 pi over 6. And take the cosine. It's in the 4th quadrant. Cosine is positive. It's the x's of the point. And so therefore it is square root of 3 over 2. Plus 2 times the tangent at 4 pi over 3. Mr. Contract, I do not have a tangent on my unit circle. It is sine over cosine. So therefore, I'm going to change this to sine of 4 pi over 3 over the cosine of 4 pi over 3. This becomes square root of 3 over 2. I don't need the parentheses. Plus 2 times, what is the sine at 4 pi over 3? Where is 4 pi over 3? third quadrant, about 225 degrees. Oh, third quadrant sine is negative. And the value at the sine, which is the y, is square root of 2 over 2. The cosine value, third quadrant, is also negative, but it's also... Oh, I am wrong, guys. I was thinking 225. It's not 225, is it?
It's 240.
It's 240. Someone said the right ratio, but I was thinking pi is over 4, not pi is over 3. 240, so that ends up being square root of 3 over 2, right? A negative square root of 3 over 2. What's the cosine at 240? Or 4 pi over 3? Or 1/2. We don't want to use square roots of 1 anymore. You should have it fixed, right? Here we go. Negative divided by negative is positive. You're dividing both of those by 2. The 2's will cancel each other out. So you're left with square root of 3 over 2 plus 2 times square root of 3. And if I wanted to put those together, I need to have, again, which is multiply the second fraction by 2 over 2. And 2 times 2 is the 4. So therefore, square root of 3 plus 4 square root 3 all over 2. We're done. No. We can simplify this more. Not dividing by 2. Yeah, add the square root of 3's. What's square root of 3 plus 4 square root of 3? 5 square root of 3 over 2. Now you're done. Our next problems, guys, has to do with geometry of circles, of spheres like the Earth, which if I took the Earth and I cut it anywhere right down the center, through the center of the Earth, I would see from a side view then a circle, right? Essentially. The Earth, I don't think is completely round. That way it's a little bit oval in shape, I think. Or it's not a perfect ball. So you would see a little bit of deviation from this, but for all intents and purposes, it'd be really close. So the question is that, say spring break came up, and I am going to Europe, say Germany. How do you get to Germany? You fly. I'm going to go visit Jan. Okay? So we're all taking a trip. We're all visiting Jan in his hometown. Das ist gut. It was on the outside of, I don't know, Munich? Is it? No, I forgot you told us one time. Okay. Anyways, but I think all of us would agree that the Earth would be a big circle, yes? We would say, hey, on Earth, we would be someplace about here. And, well, let me try to think of this. I'm going to say that I'm going to take the Earth, I'm going to find our two cities on the globe, and I'm going to cut through that Earth, right? Bless you. So that our two cities are on the same circle. So our city would be here. Germany, wherever he lives, say Munich, is there, right? This is not a perfect match. That means this Earth was cut purposely down the middle for our cities. If you wanted to actually get to Germany, would you take a straight line approach? Because the shortest distance between 2 points is a straight line. So technically, if I wanted to go from here to Germany in the shortest distance, I better get my shovel out and start digging a hole, right? Because I can't go straight there. Instead, I have to travel the path of the arc, right? From here to there. Generally, we'd even go a little bit further than that because we'd be on a plane, right? Flying above the Earth. But that's the distance that is between two towns or two cities or wherever on the Earth. It's not a straight line. Even from here to Chicago or to here, someplace in Wisconsin, you still have to deal with that. You're not necessarily going in a straight line. We're only covering short distances, so at that level, it is pretty level, flat, right? For the most part. But we all know that if you get to actually see at the ocean, you can actually see the curvature of the Earth, right? That horizon. This is what needs to take place. I'm giving you two formulas for this. They're going to look for the arc length. The arc length is the length that you would travel on the arc of a circle given a certain degree. So what they're going to do is they're going to take those two towns and link them together to the center of the circle. They're either going to tell you a degree measure between those two towns. It's 30 degrees. It's 45 degrees. It's a 120 degrees. Or they're going to say it's pi over 4. It's pi over 3. It's 3 pi over 4. Okay? So you have to know that if your central angle, remember that's the central angle, the one that's formed at the center, is it in radians or if it's in degrees? And so the arc length, the arc, is equal to, if it's in radians, it's just equal to theta, the radian measure, times the radius. Now, if we're on the Earth, I forgot what that was off the top of my head. It's like 5,000 or 6,000 miles for the circumference or the diameter of the Earth. They're going to tell you these things. So they may say something of what the radius is, and there's theta. Okay? If it's just in radians, you need theta times r. If it's not, that means you need to use the equation for arc length, but given theta is degrees, divide that by 360, because by dividing your 30 degrees by 360, it sets up a percentage. How much of the circle am I using? And do you guys recognize that the circumference of a circle is 2 pi r? That's all I care about up here is, here's the circumference. How much of that circumference am I using? I'm only using this much. And that much is represented by 30 degrees out of the 360, or the 120 out of the 360. But I got a question. If I took a look at just this piece right here, theta divided by 360 times 2 pi, would you guys be okay with me saying that's theta times 2 pi over 360? I just moved the 360 underneath 2 pi because it's multiplying. Is that okay? Would you guys agree that I could reduce those and say that's theta times pi over 180? And what was that doing? The same thing you had to do your homework last night, which was take all your degree measures and change them to radians. So wait a minute, it's theta, not 0. So what we're saying is that this first part of theta over 360 times 2 pi is changing theta to radians and using the same exact formula. It's just a sneaky way of making you do the work to find radians, and everything's fine. So you need to know those two formulas. Okay? So, the latitude of a point on Earth is the degree measure of the shortest arc, that point to the equator. It's saying that the latitude of, supposed to be, I think, Los Angeles, LA, is 34.5 degrees north of the equator. How far is Los Angeles to the equator if the diameter of the Earth is 7,920 miles? So in this case, it doesn't want to know between two towns. It just wants to know the distance from Los Angeles to the equator. It's the same exact thing. So you draw your Earth. Your Earth has an equator right down the middle, yes? That's where the equator is. I don't care where you put Los Angeles on either side. Here's LA. Someplace in North America, yes? We have the center of the circle, and the angle to the equator to Los Angeles is how far? 34.05 degrees. The radius is 7,920. Find the arc length. What's the equation I use, guys? The first one? No.
Oh, the second one.
The second one,
The distance.
because I don't have the angle in radians. So, theta over 360 times 2 pi r. Basically, I need to figure out how many degrees out of 360 that sets up the proportion to multiply to the circumference formula. How many degrees are there? Out of 360 times 2 pi radius. And now, here's a distinction that you guys need to make. This has already given you parts of the problem as a fraction. So if I was going to check this in the back of the book, more than likely it's going to be a decimal. If this would have gave me 34 instead of 34.05, then I probably would leave it in terms of pi and a fraction. Okay? So it's 34.05 divided by 360, times that by 2, times it by pi, times it by 7,920. You end up with what? You actually have to figure this out. Get it? No? Good catch, guys. Good catch. 7,920 miles is the diameter. We don't want the diameter, we want the radius. 3960? No. Is it 3960? So it's 34.05 divided by 360 times 2 times pi times 3,960. 53 point. Comes out exactly?
No. 0.37.
0.37 miles. So the distance from LA to the equator is about 2,300 or 2,300 miles. Yeah. The next part, next question, it says Theo measured the angle between the base of a building and the top of a building and received a reading of 0.6 degrees. If Theo was 4,000 feet from the base of the building, that's a long mile, that's almost a mile away, right? When he measured, the measurement was made, how high was the building? Now, at first, when I looked at this problem, I'm like, why is this in this section? But in the back here, it says, approximate using arc length. You're not going to find the exact value here. Now, why is this true? Here he stands, right? He's looking at a building over here. That building is 4,000, nope, not there. That building is 4,000 feet away. He looks to the top of that building, all the way up there, right? With a degree measure of what? 0.6. It wants to know the height of the building. Would you guys agree that this would actually be a pretty large circle? It's got a diameter of a radius of 4,000 feet. That's a big circle. Now, think of it this way. You can't see this on the video. Okay? If my hand, which is only, 2.5 feet, maybe not even, right? The end of my fingertips, if it's at ground level, and I raise it to here, there's a difference in the actual height of where my hand ends, right? Than the actual path that I take. So, I'm going to demonstrate that here. My hand is here, and I move my hand because it's so small of an arc, right? A radius. Would you guys agree that the height of my hand, the true height from level, straight up, this height that's black would be smaller in comparison to the red arc back here? That seems to be pretty accurate. Now think of it back to our idea that he's standing 4,000 feet away. 4,000 feet away. If my arm was 4,000 feet, and I only move this arm 0.6 degrees. Doesn't seem like a lot because my hand's right here, right? That's only right there, right? That's not a lot. That might even be a whole degree right there. But if I extend that out 4,000 feet, there actually is a difference or a height in that building. Can you guys see that?
Yes.
That arc that would be projected from this building, would it actually be that much further than the actual true height of the building? Do you see that those two, this height, the true height of the building, and the arc length of that big of a circle would actually be really close to the same? They won't be perfect. Because the bigger the circle gets, look, we're on the earth. If I walk across the room, now we made this level, or if I'm outside just walking on the earth, it doesn't feel like I've actually done any curving around the earth, right? For all we do, we just keep walking. If I just kept walking, I would never get this feeling that I am actually going around a circle. Why? Because the earth is so large. So we're forming this circle to be super huge, and therefore the height of the triangle or the length of the circle would be essentially almost the same. That's why they want us to use the arc length formulas. To back this up, we will use tangent to solve for h. SOHCAHTOA, it's a right triangle. We'll do things that way. So, first, I want to do arc length. And arc length, again, is 0.6 over 360 times 2 pi times 4,000. Take your calculator out. Give an answer. But here's the thing. I'm going to prove that because this circle is so large that they essentially are the same thing. I think everyone should understand that the tangent of 0.6 is h over 4,000. It says that the guy is standing 4,000 feet from the actual building. So therefore, he is at the center. The radius is 4,000 feet. So, that means h is equal to 4,000 tangent of 0.6. What is the first one? What's 0.6 divided by 360 times 2 times pi times 4,000?
41.89
feet. So the building's only like a 4-story building. Maybe even just though it's just as tall as this building or the gym. So when you can see that through almost 4/5 of a mile away, it's not going to be much of an angle up, right? What is 4,000 tangent of 0.6? Make sure you are in degrees. 41.89. Now, this only works because 4,000 feet makes a very large circle, and 0.6 is a really small angle, right? Now, if I would actually have to go 50 degrees in this circle, then this won't be the same. Large radius, small turn. Means small difference. Homework is on page 282, 1 through 2, 10 through 12. Have a great day.